Okay, so often what we do, we always like to use the mathematical software to calculate the various calculations. Okay, you are computer engineers and you are probably thinking that, okay, uh, since it is a mathematics class, so we need to do calculations manually. And actually, sir is pressurizing us to do the calculations manually. But nowadays most of the we have many softwares, mathematical softwares like Maple, MATLAB, Mathematica. I mean, many softwares are there where which we can use to calculate these eigenvalues and eigenvectors corresponding to a given matrix. We can easily calculate, and it is right. You are of course right that we can easily calculate them using mathematical software. But I am going to show you a fallacy that will occur when I am trying to do the calculation using the software. So you are going to see it right now, that why we most of the time we will not be, I mean, we cannot depend on the softwares always. Sometimes some concepts remain vague when it is discussed, when we try to do it through softwares. Your computer program uh, cannot define everything which is true in mathematics, in a mathematical sense. So that I'm going to present right now. Hope my screen is visible to all of you.
Yes, sir.
Okay, so the mathematical software that I'm going to use is the following. It is Maple. So I'm opening this software. I'm going to calculate the eigenvalue and eigenvector using this software. Now, I will consider a new document where I'm going to write this term with linear algebra, and the linear algebra calculations are getting activated over here. I want to calculate the eigenvalue and eigenvector of the given matrix that I calculated manually. So my matrix that I want to feed into the software first of all. Okay, so my matrix was of order 2 by 2. So it is a zero field matrix. Okay, and I'm going to change the terms one by one that you have to manually enter, just like we give input to the computer program. And this was my matrix 1141, whose eigenvalues and eigenvectors were found. Okay, if we do not put this semicolon sign, already it has been fed, but if we miss this semicolon sign, then some error will creep in. So this is my matrix. Now what I'm going to do, I'm going to select the matrix and click on the right button of the mouse. You see these options are coming: eigenvalues, eigenvectors, singular values, characteristic polynomial. If you click on eigenvalues, it will only calculate the eigenvalues. So you see the eigenvalues are getting calculated. My eigenvalues were 3. We got the eigenvalues as 3 minus 1. And you know that any vector is actually represented in the column vector form. This is the actual representation. I talked about it in the last class. So they have written it in a column vector form. Okay. But if you need the eigenvalues, then you have to select the matrix and you have to click on that. If you click on this particular thing, it will show you not only the eigenvectors, it will also show you the corresponding eigenvalues. So you see what is happening. Now we want to connect the result with the software. What did we get in the calculation? In the calculation we got, at one stage, we got V1 is equal to minus half V2. And at another stage, we got V1 is equal to half V2. I, in my case, wrote it in the reverse way. I wrote V2 equal to twice V1 and V2 equal to minus 2 V1. So in my case, the vectors came out to be v1 into 1, 2, and here it came out to be v1 into 1 minus 2. But in yeah, and but in their case, the thing will be kind of different. Although their meaning they will retain the same meaning. So the vector will be here v2 has got the independent choice. So they will write v2, and here they will write minus half v2. Here they will write v2, and here they will write half v2. And then what they are doing, they are taking v2 common, and they are writing minus half and 1, and they are taking v2 common, they are writing half and 1. How to read this particular thing? They have written it in this manner and matrix in this manner. How to read it out? According to the software, connect this eigenvalue with this eigenvector, connect that eigenvalue with that eigenvector. This is the way by which it is read. These two are connected, and these two are connected. And I also told you that in my case, if I stick to their form, so corresponding NLA lambda minus 1, that would be what? That would be all the vectors of the form minus t into minus half 1 colon t belonging to R. And NLA corresponding to lambda 3, that would be all such vectors of the form half and 1 t into half 1 such that t belonging to R. But now you see the fallacy, I mean the defect of these softwares, and this is not only for Maple and the Mathematic or MATLAB, it is for any software, that here the set is actually infinite. This infinite set of eigenvectors. Here the set is actually infinite. But here they are only showing you the special case of the eigenvectors only. They are showing you the special case of the eigenvectors. They are showing you minus half 1 and half 1. They are considering t equal to 1, t equal to 1, and t in both the cases. Okay, so that minus half and 1 and half 1, they are standard ordered basis. All the elements of this particular set. What is the basis of this? What is basis of LA? The basis of LA actually, if you carefully observe, the basis of LA is actually here minus half 1 and half 1. And the elements here are the linear combination or of these particular vectors. Okay, so you see they have just written here the basis. But if anybody learns, obviously minus half 1 and half 1 are the eigenvectors of this particular square matrix. But if anybody doesn't study the book and do the calculation by themselves manually, they will think.
Sir, I did not understand the defect. I mean, it looks all right.
Now, defect is that, say, I am teaching you the concept of eigenvalues and eigenvectors through software. Forget about everything that I discussed from the previous 2 sessions. Suppose I'm starting from this particular class, and I'm showing you that, okay, this is the square matrix. This is how the eigenvalues are calculated, and these are the eigenvectors. A person who is not well aware of the mathematics, who only does physics, he doesn't have any interest in knowing all the manual details. He will say me that, okay, just give me the software and tell me how the software operates. I will say that, okay, this is the matrix, this is the eigenvector, this is the eigenvalue, and these are the eigenvectors. What will he interpret? He will interpret that minus 1 has only one eigenvector, which is minus half 1. 3 will have only one eigenvector, that is half and 1. But in the software, it is not saying that actually eigenvector is of this type, linear combination of this. Actually, minus 1 has infinitely many eigenvectors of this form. Any multiple of minus half 1 is the eigenvector of minus 1. Any multiple of half 1 is the eigenvector of lambda equals to 3. So it is a misinterpretation. They may misinterpret the thing. They may think that eigenvectors are always unique, corresponding to a particular eigenvalue, but it is not. For a corresponding eigenvalue, there may exist many eigenvectors. This is the fallacy of this particular software that is happening with. Have you understood what is the fallacy?
Yes, sir. Yes.
Okay.
Yes, sir.
But since you have already known the fact, since you have already done the mathematical calculation, you know everything. You know basis, you know dimension, you know what is LA, you know everything, kernel of T, everything you know. Immediately by looking into the software, and if I'm playing the software in the third session, so immediately by looking into it, you will say that, oh, okay, fine, sir, we understood. Actually, there are infinitely many eigenvectors corresponding to the given eigenvalue, but here they are considering the basis only. They are considering the basis only, whose linear combination can be considered. So they are taking t equal to 1, and just like we write the coordinate xy as x into 1, 0 plus y into 0, 1. Now 1, 0 and 0, 1 becomes basis. So this is the basis actually. They're writing the basis of the eigenvectors. Understood?
Yes, sir.
Yeah. So this is the fallacy. So this is the defect of the software. So never try to learn anything from the software. The algorithm of the methodology has not been written in a way so that the particular person who is learning from the software, he will identify everything of the concept. Software gives a glimpse of the main parts of the main concept. They do not give you the concept at all. So some person have written this particular algo and feed it into the this particular mathematical software, but he couldn't write a algo, couldn't write a program which will show me everything related to this particular eigenvalues and eigenvectors. So interpretation may become vary if a person starts with this software. But if you learn the book, if you learn it, do it manually, and then you come back to software, you will not be having any problem. So softwares are designed keeping in mind that whoever is using the software, he knows the concepts very well. So that I wanted to show you in my first part of the last session. And now I'm going back to my whiteboard, and I'm going to connect the diagonalizability with which I started the class with the concept of eigenvalues and eigenvectors. So it is said, there is a very important theorem which says that this is a connection, actually, connection of the two. It says that a linear operator capital T on a finite dimensional vector space V is diagonalizable if and only if there exists an ordered basis beta for V. Probably you are thinking, sir is writing the same thing again and again. Now here is a change consisting of eigenvectors of capital T. So if you can find you may know for a particular vector space, there may exist many bases. If you can find an ordered basis which is constituted of the basis elements are the eigenvectors. not just any vectors. These are the eigenvectors. So therefore, such a basis, the existence of such a basis will, will give us, put a stamp on the fact that the corresponding linear operator is diagonalizable. If you are not able to find any such basis containing eigenvectors of the linear transformation, then you will not be able to say that it is diagonalizable at all. So the connection between the diagonalizability of the linear transformation or corresponding matrix representation and eigenvector is that if we can find an ordered basis consisting of the eigenvector of the transformation, then the transformation is diagonalizable or operator is diagonalizable. So in our case, we have got the basis as 1, 2. I'm writing in my way, 1, 2 and 1 minus 2. This is the basis that I've got. We can very easily show that these are linearly independent. Try to show that it is linearly independent. Not now, later you show it is linearly independent, and span of beta is equal to V actually. Span of beta is equal to V. Try to show these two things and confirm the fact that it is indeed, beta is indeed a basis containing these eigenvectors. So we will say, if we can show this particular thing, we will immediately say that the given matrix capital A, which is 1, 1, 4, 1, this matrix is a diagonalizable matrix. If you can show that beta is a basis containing these eigenvectors, then I will say that capital A is a diagonalizable matrix. So now, if it is a diagonalizable matrix, the how to find that diagonal matrix, that is the important. What is the diagonal representation of the matrix? So quickly speaking, I'm saying that you will be able to show that beta is a basis. Indeed, beta is a basis for the vector space. You can easily show it. Now what happens is that this is the part, this is the existence of diagonalizability. Okay, and the next part is, what is the diagonal matrix? If the diagonalizability is there, what is the corresponding diagonal matrix? So I'm quickly saying, it is already time. The working criteria is very simple. Not simple as I'm saying, it is difficult. Concept is very difficult. But right now before I finish the class, I'm saying it briefly. In the next class, we'll continue further on that. We construct a matrix Q, which contains the column, which are actually the eigenvectors, of the matrix, of the given matrix, of the transformation. Then you calculate Q inverse AQ. Find Q inverse AQ. Okay, so we know what A is. We know A is 1, 1, 4, 1. We know Q is 1, 2, 1 minus 2. We want to find Q inverse only. Okay, so we can do it quickly. I'm doing it by my software quickly, the inverse of the given matrix. I'm also trying to show it to you. If you have time, I'll make it fast. Just a minute. So I'm naming it, I'm deleting that. My matrix now, my Q matrix is this one. Here the software plays actually very fantastic role. They help us to reduce the size of the calculation. They help us in doing calculations that they can do very well. I can save some time, but if it is a matter of concept, then they are actually not very much faithful. This is the matrix. Select the matrix, find the matrix inverse, see standard operation inverse. It will be half 1/4 minus 1/4. Half. Let me write it over here. Half 1/4 minus 1/4. Okay. So I'm going back to my whiteboard. So this is half 1/4 minus 1/4. And quickly tell me, if you do this matrix multiplications, you can start with these two matrix and then you can multiply with this one, or you can start doing multiplying this and you can multiply with the right hand side by this matrix from the right hand side. Tell me quickly what matrix you are getting. Do the calculation. I can do it by using software, but I don't want to use it anymore. So just tell me what matrix you are getting. And
First element 3.
First element 3, then
Minus
where? Here.
in row, sir.
First row, second column.
First row, second column.
No, you are saying me the entire answer, final answer.
Sir,
No,
last
sir.
2, multiplication of last 2.
No, you give me the final answer.
Okay.
It has to be diagonal.
So -1.
-1. So you see the given matrix is diagonal matrix. It is the diagonal matrix. And very interesting to show is that since this matrix is diagonalizable, its diagonal elements, I mean, this is diagonalizable matrix. Its diagonal representation is this one. And in the diagonal matrix, the diagonal represents the eigenvalues of the given matrix A. Very interesting connection. Started with capital A, it is diagonalizable. This is your working criteria that I have used over here. Matrix is diagonalizable. Diagonal representation of the matrix have been found. Now you probably are thinking that why Q inverse AQ and why not Q AQ inverse. So we'll talk about it later on. Okay, so this is a working criteria. I'm saying you have to believe in that criteria. And if I apply this working criteria, then D is the diagonal representation of the given matrix. And in the diagonal representation, the diagonal elements are the eigenvalues of the given matrix. So very interesting fact that we have observed over here. So this is all about my today's discussion. I'm ending the class at this point, and as you have got my notifications on the previous day that I'll be taking one MCQ type of examination on, I said Monday, na? Monday.
Yes, sir.
Yes.
Okay, Monday evening. So you just these topics that I have discussed today, that it will be not there in the examination. The examination syllabus is has been already been told to you in the WhatsApp group. Okay, and after the examination, we will continue with the other topics related to diagonalizability and the remaining topic, that is the inner product space and etc. and all. So I'm ending my today's class. Thank you for joining. See you in the next class, and best of luck for the examination. Bye.
Thank you, sir. Bye.
Thank you, sir.
Sir.